They are among the most powerful forces on Earth, with swirling winds of more than 300 miles per hour and the strength to destroy nearly everything in their path. They account for 60 deaths and millions of dollars in property damage each year. They're called whirlwinds, funnels, twisters. These are tornadoes.
You can feel the ground shaking. Feels like a continuous small earthquake. Suddenly I realized that everything around me began to just suddenly started to lift. And I had debris hitting the car, and things were lifting and lifting and lifting, and it's coming right at us. And I'm not gonna see my wife, I'm not gonna see my daughter again. And I thought, oh my gosh, I'm gonna lose my life out here.
From the British Isles to the French countryside to the heartland of the United States, tornadoes have been tearing up the landscape, decimating buildings, homes, and entire communities. Now, there is growing concern that the number of twisters and the regions they encompass may be changing, due largely in part to the effects of global warming. Fortunately, advances in science and technology are also on the rise, giving government agencies and broadcasters increasingly more time to warn the public of impending disaster. Will new science in weather forecasting help mitigate this increasing threat? They can occur wherever cold, dry air hits moist, warm air high in the atmosphere. Tornadoes have touched down in every continent except Antarctica, appearing where you least expect them.
There are a few dozen cases a year in France, and roughly speaking, almost 95% of tornadoes in France are of low intensity, with winds estimated at less than 200 kilometers per hour. Violent tornadoes, even if they are exceptional, can occur in France. There is no construction that is completely safe from these phenomena.
But of all the tornadoes on planet Earth, most are happening in a region of the United States known as Tornado Alley, where an estimated 75% of the world's tornadoes take place, an average of more than 1,000 twisters every year, 4 times more than in all of Europe.
The central part of the United States is really the perfect laboratory to create the storms that make tornadoes. We have lots of warm, moist air that comes up from the Gulf of Mexico, and lots of cold, dry air that comes over from the Rocky Mountains. And those are the ingredients that allow us to get thunderstorms, that warm, moist air underneath that cold, dry air. But we also have the winds changing direction with height, coming from out of the south at low levels and out of the west from over the mountains. And that produces the kind of storms that actually rotate, that are much more likely to make thunderstorms that'll produce tornadoes. And it's really the only place on the planet where that happens a lot of the time.
Tornadoes get their energy from thunderstorms, and thunderstorms get their energy from the warming that occurs during the day, a bit like a hot air balloon. It rises because it is warmer than the air around it, and therefore thunderstorms will form precisely when we have air close to the ground, which is really heated, which will rise, and as long as it is warmer than the air around it, it will continue to rise. So it will form the cloud, and then the cloud, which will be able to extend to the top of the troposphere at more than 10, 12, sometimes even 14 kilometers of altitude. And so, as the day goes on, the energy is stored near the ground. This is where thunderstorms will mainly occur. All the violent phenomena associated with thunderstorms, such as tornadoes, gusts of wind, heavy hail, or heavy rain.
Central Oklahoma is a fertile breeding ground that produces more tornadoes per square mile than anywhere else on Earth. It is a place husband and wife storm trackers Val and Amy Custer call home. They live in the city of Stillwater with their 6 kids.
I have to be willing to switch gears from being a mom and a homeschool teacher to a storm tracker in the field. Usually we start our day off looking at computer models, especially when we've been looking ahead for a week or so out and we see see trends that might lead us to believe there could be a potential storm chase day coming up.
Growing up, I really liked weather. As I got older, that grew, and eventually it led to having a passion to chase storms and having a passion to warn people and try to keep people safe.
I really think I got the bug for storm chasing when I was a child growing up in southwest Oklahoma. There is just wide open plains there, and it's just so fantastic because you would see the storms come in from the Texas Panhandle, and to me it was always very exciting.
Landing an internship at KWTV Channel 9 in Oklahoma City, Amy met Val Castor.
We started a really great friendship, and so much so that he wanted me to chase storms with him. One day we were chasing storms in the Texas Panhandle, and we were coming back into Oklahoma, and he pulled off on the side of the road and jumped out of the truck, and he asked me to marry him.
I wished it could have been in front of a tornado. That would have been so awesome, right? Proposing in front of a tornado, but then we would have had to have somebody on camera to get it.
Early this morning over in Norman, Oklahoma, meteorologist and storm researcher Eric Rasmussen begins his workday.
First thing we do really is to turn on the computer and start looking at the weather data. Before breakfast even, we look at all the satellite images and we look at all the computer model outputs and try to get a sense of what the target region might be.
Eric and his colleagues work at the National Severe Storm Laboratory and the National Storm Prediction Center in Norman, Oklahoma, part of the United States government's National Oceanic and Atmospheric Administration, or NOAA.
The folks in the Storm Prediction Center are continually monitoring the weather from all across the United States, including the radars, the computer guidance, all the surface observations. So they're keenly focused on how those conditions are evolving and whether or not it will be necessary to issue a severe thunderstorm or tornado watch, which they would then send out to the appropriate forecast offices and to the media.
After decades of being dismissed by more mainstream weather data collecting sources, storm trackers like Val and Amy have become an integral part of tornado warning operations of the National Weather Service.
As storm chasers, our primary role is to warn the public about severe weather. And when we go out, we always take a moment and we pray for the people of Oklahoma, because what we do in the field is very important.
Val and Amy are assisted in their hunt for tornadoes by the high-tech equipment in their mobile truck, including a rooftop camera controlled by a joystick.
I have the ability to turn the camera 360 degrees, and why that is so important is because when a storm is back behind the truck and we're having to adjust our road options and go with the flow of the storm, sometimes we're having to drive away from it, sometimes we're driving toward it.
We also have a computer that's mounted there with a GPS readout on it. In the truck, we also have Wi-Fi. And the Wi-Fi allows us to see the radar and see it in real time. Sometimes, that is a lifesaver as far as we're concerned.
We also use a computer where I do a lot of video editing,
Exactly.
And that video gets sent back to News 9 to be used on the air. We work closely with David Payne, Chief Meteorologist at News 9, and he will just collaborate with us, and we'll talk about where he wants us placed, where we might need other chasers placed. The goal is to always try to be in the best spot with the strongest storm.
David Payne is the chief meteorologist at Channel 9 KWTV in Oklahoma City. The station has long been considered a pioneer in severe weather coverage.
I was born and raised here in Oklahoma. Whenever there was any chance of storms or any severe weather growing up, I was so glued to the TV set, and I just wanted to see what was going on, and always has been such a big part of my DNA. The one thing about Oklahoma weather is how violent our weather can become. We have more tornadoes per square mile than any other place on the planet. Every day, the daily task is to give people the most accurate, the best information on where the life-threatening weather is, where these tornadoes are.
Most mornings, me and David will talk. I'll get his opinion about where he thinks things are going to happen. I really think Northwest Oklahoma is where it's at. David said, yep, I completely agree with that.
We'll look at all the different weather parameters, and we'll pick out that tornado target together. I want Val to be in that spot.
Using computer models and live radar, Val and Amy head out towards a severe storm system that is forming in rural Oklahoma. Damaging winds, large hail and tornadoes are predicted for the area. While most people under these circumstances would be heading away from the danger, these adventurers drive directly towards it. While en route, they will communicate their observations and feed live video to a local office of the National Weather Service, reaching the Storm Prediction Center in Norman. The Storm Prediction Center is often the nation's first line of defense against severe weather. Here, forecasters monitor weather conditions across the U.S. and relay forecasts of severe weather up to 8 days in advance. They search the skies for specific rotating thunderstorms where most tornadoes are born. The king of all storm clouds, known as supercells. It begins when warm, moist air blows under cooler air. These strong winds collide, start to spin, and create supercells. For a supercell to produce a tornado, its horizontal wind motion must go vertical, where a funnel extends from the clouds to the ground. Yet few supercells actually produce tornadoes.
I think the holy grail is to figure out how tornadoes form in supercell storms. We've known for a long time that the rotation is going on a few thousand feet above the ground, but we haven't been able to make that connection between the rotation aloft and the tornado at the surface. So just about everything we're focusing on right now has to do with how that creates the tornado.
It's very complicated to have a tornado form because, in fact, in the supercell, you have to have a balance between the updraft that comes to feed the supercell and this downdraft from the other side. And why not all supercells cause tornadoes?
The main driver in that thunderstorm is the updraft, okay? So the very first thing we do is we look for the updraft as it's going up. Typically it might be, I don't know, anywhere between 1,000 and 2,000 feet above the surface, let's say, but that's what we call the updraft base. That's where all the action happens. We locate what we think is the strongest thunderstorm updraft, the one that's going to eventually take over and become dominant, and we find that and we do our best to get under it. They're not just in one spot, they're moving at forward speeds of 20 to 50 miles an hour. We get under it, we stay with it, we're watching it close for signs of rotation.
On this particular morning, the forecast calls for the high probability that a series of dangerous twisters will be forming in the region of Oklahoma, where storm trackers Val and Amy are headed. Forecasters at the Storm Prediction Center discuss conditions with local weather offices and issue a watch, notifying people in the affected area to stay alert for changing weather conditions and probable warnings.
So the tornado watch is issued quite a few hours in advance of the expected tornadoes. The idea is that there's quite a few people that need to know that there may be tornadoes later that day. You're talking about emergency managers that have to get equipment put into place, like rescue people, hospitals that may need to make preparations for moving patients, and even the weather service offices need to know that the experts think there may be tornadoes so they can pay more attention to the conditions in their local area.
As storm trackers Val and Amy Castor advance, the clouds darken, the winds begin to howl, the sky opens up, and baseball-sized hail begins to rain down upon them. Undaunted, the pair pushes forward. When Amy looks around through the truck's rotating camera, she locks onto a sight they've been waiting for. It's a massive, swirling, cone-shaped tornado descending from the heavens and heading towards a small town directly in its path. Out in the field, Val and Amy Castor catch the first images of a tornado bearing down on a small town in Oklahoma. Val immediately contacts meteorologist David Payne back at Channel 9 studios.
I'll start yelling, tornado on the ground, tornado on the ground. And they know that they're gonna have to do a cut-in really, really quick. This tornado is a half a mile north of Highway 33. It is moving straight east. It looks like it might be 200 yards wide at the ground. It's moving towards the town of Kingfisher.
Using GPS, the storm chasers take off in pursuit.
When we first see that tornado touch down, I get pretty excited. There is so much going on at that moment that it can seem a little overwhelming. I'm looking at the camera. The shot needs to look great. The roads that we're navigating need to be checked out. We need to make sure that there's no bridges out. Sometimes I just have to look away from the camera lens and look at it, you know, just through the windshield and just kind of take it all in, because really the camera just does not do it justice.
They send a live feed of the threatening twister to Channel 9 as David Payne is on the air.
Look at that debris cloud.
Yeah.
Man, David,
Yeah.
this thing got big and strong fast. This
Large.
is not a weak tornado, David.
No. And there you go. The meteorologists in the weather center are talking back and forth to me, telling me this is what's going on with this tracker, this is what's going on with the chopper. So many moving parts. And I've often called it controlled chaos, because you have to stay ahead of what's happening. And my job is to give people at home the quickest and earliest warning that I can.
Outside the studio is the station's own unique dual polarization Doppler weather radar. David assesses the information provided by the radar, as well as data from a model-based computer forecasting system known as MAX.
Gosh, when I first started back in the day, I mean, you would look at a piece of paper that came out in the morning and the evening, and it would tell you whether there might be possibly a storm or a higher relative humidity. I mean, that was it. And now the modeling is getting to where now we can take radar data, it's instantly ingested into the model, and it will give you where that storm is going to be in the next 5, 10, 15, 20, and 30 minutes. We need the data to be instantaneous. So the radar is always live. There's no delay for us. You're able to give the viewer at home, through the use of your storm trackers, your chopper, and your radar, the exact location of that tornado. We will make that call on. And I know that when I say, hey, this is going to be a News 9 tornado warning.
The local branch of the National Weather Service also issues a tornado warning to the community. A twister is imminent. Time is essential.
Today, for tornado event, the average lead time is about 13 to 18 minutes. What our warning system is designed to do today is to offer people the opportunity to shelter in place. And unfortunately, there isn't a lot of time to do much more than that.
But what if it were possible to give people more time to make those individual choices, to stay and shelter in place or evacuate?
So it might be the case that A lot of people actually would prefer to get out of harm's way if it was possible to do so before a tornado strikes an area. If they were to do something like that, then they would need a lot more than 13 to 15 minutes to get out of the way safely. It would be really helpful if those individuals who would want to make those choices had information that targeted the time scale when they need to actually be making those decisions.
Weather values have no intrinsic value by themselves. They acquire value by being used by people to make decisions. How do people make the right decisions that ultimately leads to the saving of life and less damage to property?
Those are the kinds of questions being addressed at the National Severe Storms Laboratory, the research and development arm of the National Weather Service. When the Weather Service issues a tornado warning for a very large area, everyone within that area gets the same message. It's possible to get a severe thunderstorm or tornado warning while standing under clear skies. With less of an incentive for people to take any action, complacency can be the enemy when the next tornado strikes.
We can produce the best forecast possible, but if people don't take appropriate action, then it doesn't matter. So that's why we have to do things like social science research to make sure that the information that we give them is actionable so we can save lives and property.
Cody Berry, a research scientist at the National Severe Storms Lab, is leading a program to address the next generation of severe weather warnings, forecasting a continuum of environmental threats, or facets, seeks to fine-tune exact storm threats to specific areas. But facets is more than just the measure of science. It's also a study into human behavior.
Research at the National Severe Storms Laboratory has asked forecasters what goes into making a warning decision and have found that there actually is a social component to making that decision, that they are considering what is going on in society as they make that decision. In order for facets to be successful, we have to integrate social and behavioral sciences with the physical sciences in order to create actionable information for our end users.
Those are the kinds of questions being addressed at the National Severe Storms Laboratory, one of the research and development facilities of NOAA. The grids are actively moving in real time and assessing threats down to the exact streets. It's a very personal forecast, telling you exactly what the threat is at your location.
One of our areas of research is threats in motion, which is essentially taking the warning polygon that we currently have and moving it with the storm instead of it being stationary. So what that does is it gives people that are upstream of the warning polygon more advanced notice that a storm is coming if they aren't being weather aware. That when you're in the warning, you need to take action. Those that are outside the warning but are at increasing chances of being hit by a tornado, they can take their action at a lower threshold. What I envision for future tornado warnings is that once the National Weather Service forecaster issues that warning, it gets disseminated through a variety of methods. And that would include things like wireless emergency alerts on cell phones. That would include broadcast meteorologists on television communicating the current status of the weather situation and the warning. And it would also include third-party apps through private sector companies that can tailor those warnings to their individual users.
As technology develops, people and places at high tornado risk around the world will have the ability to receive targeted warnings sooner and more efficiently to help make their own decisions.
In France, we do not have a system such as those designed in the United States. So we're going to have the monitoring map that has existed since autumn 2001, which will warn about various severe weather phenomena. In France, there are generally between 20 and 50 cases of tornadoes each year. And these times are rather situated in the hot season, rather from May to October. And therefore, the regions in France, which will be mainly concerned by tornadoes, will be located on the northwestern quarter of the country, but also close to the Mediterranean regions. On the night of August 3rd, 2008, thunderstorm cells are developing. And very quickly, these storm cells get stronger. They take on a rather peculiar shape and look just like supercells. So, at that time, it must be admitted that people were not necessarily aware of the risk of tornadoes and of these supercells. Shortly after 10 p.m., there was a tornado. And this tornado has reached an extremely strong intensity since it was estimated at EF4, with wind gusts that must have approached 300 kilometers per hour. Unfortunately, this tornado passed over an urbanized area, and so inevitably, there were dramatic consequences.
There are other regions in the world where tornadoes can be a significant problem, and they really haven't been studied enough for us to understand, how major the problem is. But for example, places like Bangladesh appear to have some pretty strong and large and violent tornadoes, kind of similar or sometimes maybe even worse than what we tend to see in the central U.S.
So the North Indian subcontinent, especially the eastern part of it, is peculiarly prone to tornadoes. In fact, outside of the United States, this is the region that sees the most severe tornadoes, especially during April to June period. The primary reason is that we have a dry line between the dry westerlies with the moist southeasterlies from the Bay of Bengal. And in the upper levels, generally during this season, there is the westerly, subtropical westerly jet stream that comes over this region. Along with that, there is a very cold air advection in the upper level. Very potent conditions for severe thunderstorms, especially tornadoes. Because of this, some of the most severe tornadoes of the country and of the world happen over this region.
Bangladesh, for example, is a place that gets tornadic thunderstorms. They may not get as many storms as we get in the United States, but when they happen, they can be exceptionally violent. In fact, the single deadliest tornado we know of in world history took place in Bangladesh in the late 1980s.
On April 26, 1989, the Manikganj district of Bangladesh was struck by an F5 twister, the strongest tornado on the Fujita scale.
The most severe tornado recorded in recent years was the tornado of Manikganj in Bangladesh. In that tornado, around 1,300 people died, and more than 150,000 people were displaced.
It was the deadliest tornado ever recorded in the world. Several reasons account for the extremely high death toll.
The reason was mainly that over these regions, the houses are mostly with corrugated roofs, and temporary structures are more common. So in case of a tornado, these temporary structures are blown off and they become projectiles. So these cause more damages than expected. Problems that are there are epidemics, there are injuries, because of which also a lot of death and damages happen. There has been a lot of improvement both in India as well as the neighboring countries. One of the most significant improvements was the formation of the SARC storm project, under which a lot of data was exchanged or is still being exchanged between countries which have, neighboring countries which have a similar kind of problem during the period March to June. So during that period, the observations are shared amongst countries. If we expect people to take action, the action has to be communicated to them in time for them to act upon it. So 3 hourly nowcasts for thunderstorms, their severity, likely impact is communicated in India up to the district level and block level, which is as close as possible to the people, to the disaster managers, so that action can be taken and damages can be averted. With all these actions, we are seeing significant improvements, increasing awareness amongst the people.
Back in Oklahoma, while David Payne tracks the moving storm, Val and Amy are chasing the twister that's about to strike the town.
They like to get in close. And there are times where I'll be on the air, you know, and I'll kind of sweat a little bit and think, man, he is right there. He's in harm's way, but he's good. And he knows how to get out of the way.
I want to try and get us as close as possible to that tornado and still stay safe, all right? So close, but safe. I'm always about 10 miles ahead, looking at the map, deciding where to go.
In 2013, the El Reno tornado struck central Oklahoma with wind speeds of 165 miles per hour. Val and Amy were there.
We start getting hail, and the hail starts off as golf ball size, and then goes up to softball size hail. Just bam, 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 hail just falling all over the place, can't see much. And then all of a sudden, boom, we pop out of the rain and the hail core, and there's this massive multiple vortex tornado on the ground to our east. I mean, several, like 3 subvortices just spinning around, kicking up dirt, and I'm looking at it, the largest tornado ever recorded. It's getting bigger and expanding over top of us. So we're backing up. Other storm chasers are turning around and leaving. We're getting winds flowing from the west to the east that's shaking our truck, kind of making us feel like we're floating on air, and that wind was flowing into it. That was a dangerous situation. Our pastor, Pastor Hardy at our church, sent this text, and obviously he was watching Channel 9 coverage, and the text went like this. Channel 9 has plenty of storm chasers, but your kids only have one, mommy and daddy. And then the second part of that text was, listen to your pastor.
Sudden changes in direction and rapid enlargement caught many off guard. 3 veteran storm trackers were killed.
Our job is extremely dangerous, but we have to be smart and use our experience and be wise about every decision we make, because we do want to make it home safe to our kids.
Many Oklahomans are descendants of generations that have grown up under the threat of tornadoes. For Val and Amy Castor, storm tracking is more than just a job. It's personal.
And so we were watching that storm that formed out west of Stillwater, and that thing quickly got strong. Obviously, you know, our house is in Stillwater, and I called the babysitter, and I said, okay, I want you guys to get in the cellar right now. So she got all the kids, they went out to the cellar.
As a mother, it was just horrifying.
For the scientists who study them, getting too close to tornadoes has always been a risky business.
Thunderstorms that produce tornadoes. This is an exceptionally dangerous place to try to collect data. Just above the ground, and with air coming down, potentially large hail in the area. It's just a very dangerous place to be. And so this has been one of our big limitations for a long time.
Prior to the tornadoes forming, there's a rotating column of air that extends all the way to the ground. But somehow the storm is concentrating that into a very small column, which becomes the tornado. And it's probably the mechanism as same as a figure skater bringing in their arms and bringing that angular rotation, that momentum inward, and causing it to spin more and more quickly. Just north of that rotating updraft in the Supercell is where all the action seems to be in terms of developing the tornado. We've never operated there before because basically there's often baseballs falling from the sky, and because we didn't know there was anything interesting going on there.
Computer models are only as good as the data that's put into them. So, in the spring of 2019, the National Severe Storms Laboratory and several partners launched TORUS, targeted observations using radar and unmanned aircraft in supercells. Meteorologist Erik Rasmussen, one of the foremost tornado researchers in the country, is the NSSL's principal investigator for the project.
So TORUS has taken this approach where we're going to observe the supercell and the area right around where the tornado forms a lot better than we have in the past. If we understand those processes are going on, say, within 1 to 10 miles from the tornado, we can probably infer how they contributed to the development of the tornado itself.
The TORUS project is a uniquely scientific undertaking covering approximately 367,000 square miles, from Texas to South Dakota.
So what we're bringing together in TORUS is some new combinations of instruments. The NOAA Hurricane Hunter aircraft with its airborne Dopplers looking at the storm as they fly back and forth all day long. And another thing we're bringing in here is UAV aircraft that fly back and forth adjacent to the storm's rotation. Mobile mesonettes. These are big hardened vehicles like trucks with weather instruments on top. We can actually put multiple weather balloons in the air at once. And so that gives you kind of a swarm of observations around the low-level circulation and give us a whole bunch of really crucial observations of temperature, pressure, and humidity where we've never had them before. Those are new things that probably are going to give us pretty strong clues as to how the tornado is forming within the supercell.
NOAA is contributing its P-3 Hurricane Hunter aircraft to the project. As scientists fly close to the storms, they deploy global positioning systems or drop windsondes. They scan them with weather radars on board, giving them a detailed look at the structure of the storms and their intensity.
We're looking very close to where the tornado forms and trying to find out exactly how that happens and how the rotation on the horizontal axis gets turned into a tornado. We think it comes from a little pocket of intense rain or hail that forms miles away from that developing tornado and gives rise to this sort of motion. What makes a storm capable of producing those pockets of precipitation? What's the wind shear? How does the wind change with height in the atmosphere? If we can understand how those three steps hook together, now we have much better tornado forecasts out to maybe 30 or 40 minutes.
Back on the road, still in pursuit, Val and Amy watch as the tornado rips through the neighborhood where they live, destroying houses and worrying that their own home may be next.
And so this tornado is maybe a little less than 2 miles northwest of our house before it dissipated, and there's our house in the foreground. This tornado is behind our house, and my kids saw it. They took a picture of it.
While the Castor's home is spared, others living in the town directly ahead may not be so lucky. The tornado Val and Amy had been chasing has passed completely through the town. They drive into the community to assess the damage. The widespread destruction is everywhere.
We had the opportunity to go out into the neighborhoods that were hit the hardest with the F5 force winds and do a damage survey and talk to some of the residents. Just to see the destruction, the aftermath is very difficult for us to watch because, lives are affected in ways that we don't even fathom. And the emotion that I felt was just overwhelming.
The twister has cut a swath of destruction that extends for several miles. While the devastation is vast, the human toll from tornadoes can often be higher in more rural than urban communities.
The rural communities tend not to have the same kind of communication infrastructure. If you think about how television covers storms and how large networks of people can come together to produce warning systems, that's a lot easier in a big city than it is in a rural community. Rural communities have to rely on, at times, less information to make a good decision to save themselves.
And that is particularly true in the rural southeast of the United States. Here in Lee County, Alabama, in 2019, the outcome of an EF4 tornado with 170-mile-per-hour winds killed 23 people.
For this F4 tornado is going to be about 70 miles as it went into Georgia.
The power companies indicated that approximately 116 homes were directly affected as far as that cannot receive power, and it would be somewhere within that number that were completely destroyed.
It's just the emotions. You know, when you lose a grandson, it's very hard.
We just try to put pieces back together and go on and just try and rebuild.
Kim Kluckow-McLean, lead researcher of the Behavioral Insights Unit at the National Severe Storms Lab, wants to understand how these rural areas become so deadly.
The primary focus of my work is on the human behavior aspect, where people and severe weather meet. And I try to understand how people understand the threats that could be posed by severe weather, the ways that they are able to respond, the resources they need to respond.
Kim travels to ground zero of the tornado's destructive aftermath, where she meets with the survivors, emergency managers, and meteorologists. But her first stop is the local cemetery.
There had been these wonderful memorials set up to each individual that had perished in the tornadoes. There had been children who died, and that really struck the community very, very hard. And multiple members of single families that had passed away. For me, it was really important to know something about the people that we'd lost and try to put myself there as I considered what was the forecast and warning process like for them. Were they able to prepare themselves? How might new technologies have made a difference? And in a bigger sense, I was also studying the communication system. So I was interviewing broadcast meteorologists, emergency managers, and weather service forecasters.
Within the National Severe Storms Laboratory is the Hazardous Weather Testbed, a facility where people who are developing technologies can come together with the people who might use them.
We bring National Weather Service forecasters from across the country into the same room with research meteorologists and developers, and they try out new tools and technologies to figure out how well they work within the flow of a weather service forecaster.
We have started some collaborations with entities abroad. The UK Met Service is represented, Germany, France, even Australia, and parts of Asia. They can come in and work with us as we're developing new forecast technologies and techniques. On the social science side, we've started to collaborate on messaging strategies because different countries message risk to their populations in different ways. Different meteorological services have been set up in various countries that just have different approaches that they try.
We draw a lot of inspiration from what is done by American researchers and forecasters to learn from them. In Europe, we have a laboratory that was set up about 15 years ago called the ESSL, European Severe Storms Laboratory. And this laboratory aims to try to join forces in Europe to try to improve the forecasting of thunderstorms and all the severe phenomena associated with thunderstorms. They are working closely with the American researchers at the NSSL, National Severe Storm Laboratory, and also with the best American researchers at universities. They're going to propose, for example, tools such as a European database that bring together all the severe phenomena. We are going to test new products and also compare our weather forecasting methods.
A newly published study suggests the frequency of severe tornado outbreaks has risen since 1954. Could global warming play a role?
If we look at the period from early 2011 to early 2012, we set the record for the most tornadoes in a 12-month period, immediately followed by a record for the fewest tornadoes in a 12-month period. We now have fewer days per year that produce at least one F1 tornado or stronger. But we have a lot more days that have a lot of tornadoes, say 30 or more tornadoes. These things have taken place at a time when the global temperature has been increasing.
When you look at the current database, which includes all tornado cases, effectively, we see a huge increase in the number of tornadoes over the past 10 to 15 years. It's found in Europe, but it's also found in the United States, and of course, in France. The fact that the climate is getting warmer, we want to say yes, it will warm up closer to the ground, therefore more thunderstorms, and therefore we have more risk of tornadoes. But simply what will happen, probably with climate change, is what we call the jet stream. If the jet stream is shifted slightly further north from its current position, we would indeed have less wind with altitude. We would have less energy to form violent thunderstorms. And if we have less energy to form violent thunderstorms, there is less chance that supercells will develop and therefore tornadoes. In the end, it is difficult to have a consensus on climate change and the increase in the number of tornadoes.
But a warmer climate may mean bigger tornadoes, like the EF5 that struck the city of Joplin, Missouri in 2011. This monster storm reached an extraordinary width of 1.6 kilometers. The Joplin tornado killed 158 people and caused $2.8 billion in damage. Back in Oklahoma, storm trackers Val and Amy Custer stop and walk through the destroyed town. They learn more about who survived this particular disaster and who did not.
We were walking down this one block, and I talked to somebody, and the house was gone, okay? There was just a little bit left. The bathtub was there, and as the tornado was coming, right before the tornado hit, there was a family. There was a mother and a father and 3 smaller kids, right? So what they did is they put the kids in the bathtub, and then the mother got on top of the kids, and then the father got on the very top. And I believe they tried to pull something over top of them, like a comforter or something like that. But when the tornado hit, every one of them survived, with just minimal injuries. I just attribute that, to God.
People die in tornadoes primarily in 2 different ways. One is the building collapses around them and lots of stuff falls on top of them. But the most common way is probably actually essentially getting hit by debris that's flying horizontally. So if you're inside of a home, you want to be in the lowest floor, in a small interior room, no windows. You want to get as low as you possibly can in that room. Put on a bicycle helmet. Protect your head from blunt force trauma. If you're in a mobile home, you need to get out of it. Those tend to not be very safe at all.
It's time for Val and Amy to begin their journey home and reunite with their children.
Storm chasing for us, it's more than a job, it's a calling. With all the new technology, there's always going to be a need for a storm tracker because you got to have eyes in the field. You got to have ground truth.
We're so humbled to be in a position where we can broadcast information to hundreds of thousands of people that watch, and it makes a difference in people's life. We feel like it's a calling from God.
If you can give any family a warning that something horrible or potentially could kill them is headed their way, sometimes their homes or their businesses are wiped out, and they listened and they walk out of that. That's what matters. At the end of the day, that's the only thing that matters.
Val and Amy Castor leave the site where the destructive tornado blew in from the sky. But they are content in the knowledge that they have contributed to getting the word out about this awesome force of nature and have saved lives. They are naturally created machines that operate with the energy of 10,000 nuclear bombs. They're tropical storms with wind speeds that can reach up to 230 miles per hour, capable of generating enough electricity to power the entire United States for months. They are tropical cyclones. In the Pacific Ocean, they're called typhoons, and in the Atlantic, they're called hurricanes.
That cluster of thunderstorms that came off the coast of Africa moved right through the Caribbean, moved right across Central America, and eventually developed into a named storm in the Pacific.
I've never felt anything like that in my life, no. No, that was one of the most intense, terrifying experiences I've ever had in my life.
It's like a giant engine that begins sucking heat from tropical waters to fuel itself. With winds that can reach up to 300 kilometers per hour, a hurricane is a wonder of nature. Highly destructive, complicated in design, and difficult to predict.
Hurricanes or typhoons or cyclones, they have several names, are machines, we will say, with extremely complex thermodynamics. It is a very large cloud system, naturally, which has a vortex structure, therefore something that revolves around itself. It feeds on the weather, on the vapor from the ocean. This vapor is then transformed into rain. There are objects that are hundreds of kilometers long, even up to almost 1,000 kilometers long.
The tropical cycle is really the result, in jargon, of an ocean-atmosphere coupling. There really is a transfer of energy in the form of heat and humidity between the ocean and the atmosphere. And that's what makes a cyclone live.
So hurricanes really start as a cluster of thunderstorms. We consider them areas of low pressure where actually there's rising air. As air rises, the moisture condenses into clouds.
There will be the formation of a depression at the place where the air began to rise.
L'air qui se trouve juste au-dessus de l'océan chaud, il va se charger en chaleur et en humidité au contact de l'océan.
And this will create a suction of the surrounding air, which will then move towards the depression.
Par conséquent, il va y avoir formation d'une dépression.
It's colossal. That's because there are two types of energy to consider. There is the thermal energy associated with the hurricane, and there is the kinetic energy, which is the energy associated with the wind.
When wind speeds reach 119 kilometers per hour, a hurricane is born. In the Atlantic, the official hurricane season begins on the 1st of June and lasts until the end of November.
Distinctive hurricane seasons that have everything to do with having an ocean water temperature that's warm enough to support hurricanes. Typically, we need ocean water temperature at least 27 degrees Celsius or 80 degrees Fahrenheit to support these storms.
Hurricanes primarily occur in the Caribbean Sea, the Eastern Pacific or Southern Atlantic Oceans, and the Gulf of Mexico. But the genesis of these storms is found on the African continent and the Saharan desert. Hurricanes primarily occur in the Caribbean Sea. As one of the largest deserts in the world, the Sahara covers 25% of the African continent, more than 3 million square miles. This desert's wide expanse of sand absorbs heat and then radiates vast amounts back into the atmosphere. The heat and humidity over equatorial Africa create thunderstorms. These storms travel west over the Atlantic Ocean and can organize into a tropical depression.
We saw this cluster of thunderstorms pushing off the coast of Africa. This is a tropical wave. Some people get confused when they hear wave. They're thinking the kind of wave that surfers ride in the ocean, but atmospheric waves often are just areas of disturbed weather that track through the tropics.
On August 28, 2014, a tropical wave off the African coast catches the attention of atmospheric scientists of NOAA, the National Oceanic and Atmospheric Administration of the United States. The storm is steered by the trade winds, the prevailing winds that flow permanently from east to west across the Earth's equatorial region.
That cluster of thunderstorms that came off the coast of Africa across the tropical Atlantic moved right through the Caribbean.
Los Angeles resident Jennifer Lowry has been waiting to go on a planned vacation to Cabo San Lucas, a resort city at the southern tip of Mexico's Baja California peninsula. With over 200,000 residents, Cabo is known for its beaches, outdoor restaurants, and bars.
And it was just traveling down for the weekend with two of my best girlfriends. Just a quick weekend getaway, very casual.
September 3rd, 2014. What started out as a tropical wave off West Africa is now a poorly organized storm that is slowly crossing Central America. The United States government's National Hurricane Center warns of the possibility for this wave to develop into a low-pressure area south of Mexico and later into a tropical cyclone.
The cluster of thunderstorms arrived in Central America around September 3rd, moved out into the Pacific. It became a tropical depression, which is a closed circulation, a closed area of a disturbance. It never really developed into a hurricane or a tropical storm in the Atlantic, so it never got a name. But moving out into the Pacific, it got better organized.
Yeah, so that day it was a lot of hanging out by the pool and walking down to the beach, just, again, only overhearing a couple minor conversations, but nothing, no announcements from the hotel, nothing, even on the weather radar that would indicate a threat in terms of a hurricane headed our way. But heard rumors that it was out there, but not headed in our direction. And so we just went about our day. We went down to the beach, just a happy little holiday. There was nothing indicating that there was anything amiss.
The large system of thunderstorms slowly progresses westward and gradually organizes over the next few days. An increase in thunderstorms prompts the National Hurricane Center in Miami, Florida, to upgrade the tropical depression to tropical storm status.
The winds reached 39 miles an hour, where it became a tropical storm. And they're given a name in the Pacific and the Atlantic.
The World Meteorological Society assigns the storm a name.
In this case, it got the name of Odil, late on the day of September 9th, 2014.
Storms are given first names because, in the end, it speaks more to the people. And in general, people are more attentive to phenomena when they are given a first name than, for example, a number. It was the sailors who started to give names to cyclones. The funny thing is that in the beginning they used to give female names to the cyclones they encountered. I don't know if it was because of their unpredictability, devastating nature. I don't know.
Now, Odil is starting to get noticed.
There were some rumors around the hotel, or some murmurings, that the storm was strengthening and was headed back east, so towards the Cabo Peninsula. No indication it was going to be a major disaster.
From there, Odil really started to strengthen a little bit as a tropical storm, but something really interesting from September 11th to September 13th, 2014. The forward speed had dropped and it drifted in somewhat of an erratic path. That makes it a little bit harder to forecast the direction and the intensity when storms are drifting like that.
The storm had changed course fairly rapidly. It had turned east, but was still not headed directly for the Cabo Peninsula.
But around September 13th, the steering became a little more pronounced. We had a mid-level ridge of high pressure to the east, upper-level area of low pressure to the west. And as these systems became more pronounced, it enabled Odil to have better guidance and better upper-level tracking and guidance from above, really. And that enabled the storm to start accelerating. Not only did Odil start accelerating towards the coast of the Baja Peninsula of Mexico, but it actually intensified very rapidly at that time as well.
With wind speeds increasing to over 119 kilometers per hour, Tropical Storm Odil is becoming a hurricane, capable of much more devastation.
On Saturday, or September 12th, we started hearing about the storm from some of the other people in the pool. Often kind of overheard some conversations from some other travelers saying that, oh, there was a hurricane developing in the Pacific, but it wasn't really a threat at the time. It was headed out west, but it's there, just to kind of keep an eye on. But again, at that time, it was not even on our radar. It was just kind of like, oh, there's a storm, no big deal, we'll be fine.
Odil rapidly intensified from a tropical depression to a tropical storm, and then right up to a Category 3 hurricane, which is considered a major hurricane on the Saffir-Simpson hurricane wind scale. So it became a very violent and very dangerous hurricane. The winds increased by 55 knots. That's about 63 miles an hour, or more than 100 kilometers an hour in less than 24 hours. So very rapid intensification.
The National Hurricane Center in Miami, Florida, upgrades the storm to hurricane intensity on September 13th.
And some of the other guests would say, there's no shot there's ever going to be a big storm here.
But Jennifer and her fellow resort guests in Cabo have no idea that their lives are about to change forever. What started out as a tropical wave off the West African coast lumbered across the Atlantic Ocean and Central America. Now in the Pacific Ocean, a large central area of thunderstorms has taken form, surrounding a circulating center. The National Hurricane Center designates the storm as Hurricane Odil. The initial forecast is that Odil will track westward, curving out to sea and avoiding land. In the resorts of Cabo, a minor weather alert is posted.
When we first started to hear rumors of it, or just that it was out there, nothing more than a little excitement. You know, coming from Southern California, there's not a lot of weather, so the thought of a big storm that might potentially let us have an extra day off work and stay in Mexico an extra day seemed exciting, but that's about it. Nothing dangerous, nothing fearful. We walked around the property, took pictures, and again, at that point, it was more of a novelty, like this is really, really exciting and fun. And we didn't, think there was a little bit of concern, but nothing that, we weren't fearful for our lives at that point. And there was no major reason for concern at that point.
While scientists know how a hurricane develops, they know less about what the storm is likely to do.
As soon as there is a phenomenon that begins to resemble a hurricane, researchers, especially the American researchers, since they're the ones most concerned by these hurricanes, they will begin to run models to try to forecast, to see if the hurricane will develop, and above all, to predict its trajectory.
Really, one of the limitations of forecasting sometimes is not having enough data, especially in hurricane forecasting. That helps us predict through computer modeling what it's going to do in the future.
For over half a century, information from satellites is used to track the movement of hurricanes.
Satellites allow us to measure the surface temperature of the water. They obviously allow us to monitor tropical cyclones. We can see them forming over the ocean, even though they have not yet fully developed.
Satellite advances in the last 40 or 50 years have enabled us to sample the weather through satellites, detecting cloud formations, hurricane formations, data. We don't know what's happening over time in the hurricane. Sometimes it's hard to sample these areas.
Retrieving data from battering wind speeds of 240 kilometers per hour seems almost impossible.
When a hurricane begins to threaten the United States, the Americans send planes specially designed to fly into cyclones.
Flying directly into Odil are NOAA's two P-3 Orions and a Gulfstream 4 jet for hurricane observations. These are the hurricane hunters. Manned by pilots, scientists, and researchers, these brave men and women fly straight into one of the most destructive forces of nature.
They're very valuable because they'll fly into hurricanes, they'll fly transects across the hurricanes at different elevations, sampling temperature, humidity, wind speed, all these valuable data inputs that go into our models.
On board is high-tech equipment like radar and fixed probes that measure particles in the air. Buffeted by howling winds, blinding rain, and violent drafts, these aircraft can slice through the eye wall of this monster, entering the relative calm of the storm's eye.
In the center of the storm, you have the eye of the cyclone. On average, its diameter is about 50 kilometers. So in the eye of the cyclone, there's almost no wind. In general, there are no clouds. In any case, there is no rain. Sometimes there can even be blue sky. And around this eye, there is an area where there is a lot of rain, where the winds are extremely strong. It's called the cyclone wall. And beyond this area of the cyclone wall, there are actually spiral bands, bands of rain.
Direct observations of the lower eye wall, where the strongest winds exist, help forecasters understand critical information about the storm's development, how intense the hurricane will be, and where and when it will strike land. But being so close to the ocean is too hazardous even for these aircraft to fly. So the hurricane hunters collect additional data by releasing weather devices into the storm.
They'll actually drop sensors out of the airplanes that are tethered to parachutes. They're called drop zones, and they actually go through an atmospheric column collecting data on the way down. They give us a snapshot of what's happening in the atmosphere at a certain time and at a certain location.
As dropsondes fall toward the ocean, they transmit data such as pressure, temperature, wind speed, wind direction, and moisture to scientists aboard the Hurricane Hunter aircraft.
Drop zones actually, they provide a snapshot of data in time. There's innovation and experimentation now with launching drones into hurricanes, and those do two things. If a drone can stay airborne for hours, instead of getting a snapshot like a photograph of the atmosphere, it's more like collecting a movie of the atmosphere. You're getting hours of data, and so this is giving you a lot more information. The other thing interesting about drones is that they'll often be positioned near the boundary layer where the atmosphere meets the ocean. That's a dangerous area where the Hurricane Hunter planes do not fly because the winds are really strong, and also hurricanes push towering waves, so it's really dangerous for an airplane to be near the ocean surface.
NOAA's unmanned aircraft systems have the ability to get closer and deeper inside the hurricane. The canister is released from the P-3 plane. The drone is deployed, opens its wingspan, and flies through the storm. Once it attains level flight, it begins operations. The data helps to predict the storm's maximum intensity and what's going on inside its inner core. Hurricanes are not only tracked from the air, they are also closely monitored from the sea.
Sea gliders are automated sensors that actually go into the ocean and measure data in the ocean during the time of a hurricane, so they can actually go to depths and record temperature data, salinity data, and get an idea of the oceanic profile. That's important because we know that warm water fuel hurricanes. So if your heat content goes really deep, your warm water goes deep, that actually will give you a lot more fuel over time.
Gliders are deployed in early summer and recovered at the end of the hurricane season. They collect data from ocean depths of about 305 meters. At the surface, they transmit data to NOAA's Atlantic Oceanographic and Meteorological Laboratory, which is then made available worldwide on the web.
Finally, we have more and more satellite data. We have more and more observations. We have more and more real-time data and more computing power from computers that allow us to make forecasts using numerical models. And this has enabled us to make progress, especially in forecasting the trajectory of tropical cyclones.
While projected models show Odil to be moving in a more western direction, the hurricane hunters discover it is, in fact, now moving further north.
So we're predicting a trajectory, and around that we plan an area where it might go. This is the zone that I'm going to call the zone of uncertainty. That's the forecasting cone.
Odil accelerates north-northwest in the direction of the Baja California Peninsula. Getting the forecast right can be a matter of life or death. In order to properly create forecasting models of hurricanes, scientists need to understand how they move. Help may come from a most unlikely place, like a soap bubble. A group of physicists at the University of Bordeaux discovered that when they heated hand-sized soap bubbles, vortices of color swirled into action.
Are you going to make hurricanes? Yes, you could say that. They're not exactly hurricanes, but they're hurricane-like objects, and sometimes they behave in a similar way. When it heats up, you can see that the liquid starts to stir in all directions. These vortices had a very particular dynamic in the sense that they began to rotate very slowly, and then, little by little, they rotated faster and faster. And then this speed began to decline and decrease, and that hit us right away, because hurricanes have a similar behavior.
The movement of a soap bubble vortex follows a path. By studying how these mini soap storms intensify and move, the group developed a mathematical model that can forecast, on a much grander scale, the trajectory of a tropical cyclone.
If we follow the intensity of these eddies, the wind speed in the first 40 or 50 hours, for example, for a hurricane, if we follow how it varies over time, we can predict, for example, when the maximum intensity is going to be reached and what that maximum intensity would be. We can see that in the history of these hurricanes, the variations in relation to the average trajectory, well, they are similar to what we find in the whirlpools of the soap bubble.
The objective of researchers is to better understand and finally succeed in better forecasting of tropical cyclones, hurricanes and typhoons. The objective is to better understand them in order to be able to predict them better, to forecast them earlier, to make more precise forecasts and, in any case, to be able to better warn populations that may be threatened.
When Odil makes an unexpected sharp turn north, it puts the resort city of Cabo San Lucas directly in its path. It grows into a Category 4 hurricane.
Really originally was forecast to be more out towards sea, and Odil actually stayed to the east of what was originally forecast. It became a very violent, very dangerous hurricane, tracking right towards the Baja Peninsula of Mexico and right towards Cabo San Lucas, a very populated and popular tourist area.
At that point, it was still a little fun and excitement. Really silly. Clearly not taking it, as seriously as we should. But then again, everyone else at the same time was saying that it wasn't going to be a big deal. This was fun. We would have some cocktails. We'd be stuck a day. We'd ride the storm out in our hotel. We had food. We'd watch movies. Great. No big deal.
Hurricane Odil barrels towards the resort city of Cabo San Lucas, Mexico. Foreign hotel guests like Jennifer Lowry notice the warning signs of the approaching natural disaster.
Probably at that point in time, never seen rain that severe or winds that intense. Clouds were starting to look real ominous. The tide was coming in. You could feel it in the air. Kind of everything starting to intensify. Kind of a feeling of electricity in the air. The pace of the hotel staff running around and trying to expedite preparations. They were taking precautions of boarding up the windows, battening down the hatches. Memos going out regularly to all the guests, kind of keeping us in the loop the entire time. The airlines were already talking about the potential for canceling them. So we were just kind of thinking, okay, what are we going to do? We better notify our families and our bosses and whatnot that this is a possibility that we might get stuck for a day or two. That's when it was kind of a brief hint of panic that, okay, this might be serious.
Odil started out as a hurricane, which was relatively gentle. The increase in winds was relatively slow at the beginning. And then, at a certain point, it started a very strong acceleration of the speeds. The speeds started to increase very strongly.
A hurricane will exist through the entire first layer of the atmosphere called the troposphere. The strongest winds in the hurricane will be near the ground. In order to measure and quantify the intensity of a cyclone, we can talk about its winds, the speed of its winds.
It's very important because it's this speed that does the damage. It's not the hurricane alone, but it's the speed of the winds that damages the houses, that destroys the trees.
We consider Category 3 through Category 5 as major hurricanes, capable of doing major structural damage when those winds push into coastal communities.
Odil is a Category 4 cyclone. Its winds were blowing at 220 kilometers per hour.
And even we've had some impacts of hurricanes that were Category 5s offshore, but then weakened before landfall. Category 5 wind speeds exceed 157 miles an hour. For example, Hurricane Katrina. 24 hours before landfall, Katrina had maximum sustained winds more than 175 miles an hour.
But the winds don't tell the entire story about the damage hurricanes can cause.
People think of hurricanes as wind events because we see a lot of video of palm trees blowing around and roofs blowing off houses, but it's actually the flooding that kills most of the people and does most of the economic damage. So really saltwater storm surge and heavy rainfall near the coast and inland tend to kill a lot of people and produce a lot of damage.
The storm surge is the raising of the ocean level when a tropical cyclone arrives on the coast. Winds from the cyclone push the bodies of water towards the coast, creating a rise in the water level. If ever there's a high tide phenomenon at that time, it creates an even greater rise in the water level, and this storm surge creates floods that are often deadly.
In 2012, at its peak, Hurricane Sandy stretched 900 miles along the Atlantic coast of the United States. The massive superstorm made landfall at high tide.
As it moved towards the mid-Atlantic coast, the wind field greatly expanded, and so the strong winds were blowing over hundreds of miles of coastline, but unfortunately that enabled it to push tremendous amounts of salt water all along the mid-Atlantic and the New England coast. Tremendous area got impacted by strong winds and really high saltwater storm surge as well.
The resulting storm surge was catastrophic. 346,000 homes were destroyed along the New Jersey shore. Tens of billions of dollars of damage, and a total of 285 lives were lost.
Floodwaters kill more people in hurricanes than the wind, but what we use for the classification of this storm is the wind category. And so this blindsides a lot of people. I spent about 10 to 12 years building the first storm surge database for the United States, and it's basically the comprehensive flood history for coastal communities from Texas to Maine. So it really builds that archive of data from the mid-1800s to present, so people can actually drill down into their community and actually see their community flood history, which gives us a good idea of risk analysis. Oftentimes I find people say, hey, I've lived in this place for 20 or 30 years, my property never floods. But we look back deeper into the history and we say, well, 40, 50, 100 years ago, there was a storm here that put at least, a meter or several feet of water over your property.
But there are other identifiers when it comes to coastal flooding. The evidence is not hard to find once you know where to look.
When we think of coastal flooding, sometimes we think of salt water slowly coming up. During a storm surge, the water's pushing in incredibly rapidly and it's filled with debris. And it can actually rub tree bark off of trees, and this is a sign where we can come back here and see how high the water level got.
Really, an important thing is for people to be able to assess their risk. We need both models and data for this. So the reason we need models is that hurricanes are rare events and every hurricane is different. So we need a model to get an idea of flood potential because the next hurricane is probably going to look a little bit different than all the historical ones. So we need to get an idea of what can happen in the future. That said, we need to look back into the data to get an idea of what's happened over time, because we can see high water marks that happened decades ago, or even in some areas more than a century ago. That can provide guidance to validate the models and to give us an idea where we're over-predicting or under-predicting flood risk.
Although hurricanes from a century ago were fueled by unusually warm temperatures from the Atlantic Ocean, today the Atlantic is surpassing even those temperatures and getting warmer. Are severe hurricanes destined to strike more often? The risk may be greater than we know.
2020 hurricane season broke all records for the number of named storms in the tropical North Atlantic. This had everything to do with just prime development conditions. We're seeing warmer waters in many areas. This can actually increase the number of hurricanes because we're increasing that threshold of required water temperature to support hurricanes.
In the resorts of Cabo San Lucas, at the tip of the narrow and remote Baja Peninsula, some 26,000 foreign tourists are stranded. There is no place to run.
At that point, they were grounding flights or planes on the tarmac at the airport and making them turn right back around. So all flights were grounded at that point. Around maybe 2 or 3 in the afternoon, the tide started to really kick up. The waves were crashing onto the beaches, taking out some of the little beach cabana huts. And the winds were kicking into super high gear. And the rain started to get really intense. The hotel workers were running around trying to make preparations, trying to rapidly sweep water from the courtyard because it was starting to flood. You're more than welcome to ride out the storm in your room, but if you feel safer, please come to the hotel ballroom. It's in the center of the hotel, and we have shelter for you.
In the early morning hours of September 15th, Odil reaches the shores of the Baja Peninsula.
Odil intensified from a tropical depression to a tropical storm, making landfall near Cabo San Lucas as a Category 3 hurricane with wind speeds of around 110 knots, or around 200 kilometers an hour, about 127 miles an hour.
Jennifer and her friends decide to ride out the storm in their room.
The power started to officially go out completely in our room and flicker and then go out completely. And everybody kind of went, kind of like a shriek. We're starting to get a little panicked because things were rapidly intensifying. So at that point, yes, we were in total darkness. So all communication at that point ceased. The last thing that our family members or friends heard from us were those messages saying, things are getting really bad. Just so you know where we are, we're safe, but you may not hear from us. It was starting to occur kind of in the back of our heads that what we thought was going to be fun and games and an extra day of vacation may quickly turn into worst case scenario, just at the rate that things were intensifying. The windows in the hotel room started to shake. You could start to feel your joints almost expand with the change in the pressure. The toilets and the plumbing were starting to suck water back out. So there was water coming out of the toilets and there was debris starting to come out, and everything was just, it felt like a suction. And the windows were shaking more and more. We were definitely scared, thinking, okay, now what do we do? The storm sounded like a freight train hitting the hotel. There are very, very eerie noises coming from the windows and the stairwells. There's this one sound from the stairwell that I will never, ever be able to get out of my head for as long as I live. It's the creepiest sound I've ever heard. Basically, the hurricane playing the hotel like a wind instrument. A palm tree snapped off and smashed into our window. There was water seeping through the glass panes in the window into the room. So we decided at that point this was serious enough for us to go take shelter. It took 3 of us to pull the door open because the suction was that strong at that point. And we just grabbed hands and made a run for it.
Jennifer and her friends join other guests in the hurricane shelter set up in the hotel ballroom.
There were guests that were coming in who had made it back on their own, who were bleeding and fallen, but about 80 85% of the hotel rooms were completely ruined, windows shattered. There's stories of furniture flying through the window, glass breaking. People were coming in looking horrified, injured, bloody. Once we saw the panic and concern from not only the guests who had been through hurricanes before, but the hotel staff, that's when it really started to think, okay, we may not make it. This was terrifying.
By 11 o'clock at night, the most dangerous part of the hurricane, Odil's eye wall, comes ashore. The eye wall is close to the ocean, where the strongest winds lurk. Drawing energy from heat in the water, it propels this giant monster over Cabo San Lucas.
At any moment, things could have completely collapsed. Doors of the ballroom are going to fly off, and everyone's going to get sucked out. And although that seemed like a crazy thought, that's what it felt like. The maintenance people, the hotel staff, they were continuously inspecting the roof to make sure that it wasn't about to fly off. I'd say it was the equivalent of like white knuckle gripping a steering wheel for the next 4 or 5 hours in that hotel ballroom. And then all of a sudden, it got quiet. It got really quiet, and one of the other hotel guests had their iPad up in the weather radar, and they looked, because we were still getting a little bit of Wi-Fi signal at that point. They said, "We're in the eye." And just then the hotel staff kind of came around and said, "Nobody leave the room. This is just because it's not over." But it was eerily quiet.
It can happen that the eye of the hurricane passes over an island, for example. So the wind blows and then suddenly it stops for an hour, 2 hours. So we think it's over. But in fact, the cyclone continues to advance. And suddenly, finally, it's the other part of the cyclone that's over the island. There the winds start blowing in the other direction since we're on the other side of the eye. And it's this that is particularly devastating because in the end, the houses, the facilities, etc., first suffered an extremely strong wind in one direction and then an extremely strong wind in the other. So basically, all the construction that had held up when the first part of the wall passed through will end up collapsing during the second passage.
After the eye of the storm passed by and the back wall of the hurricane hit, it felt like a bomb was going off. There were 140-mile-an-hour winds. The whole building shook. It felt like the building was just going to lift off in the air. It was much more violent and terrifying than the initial first half of the storm. And people still filtering into the ballroom, being rescued, looking like they had just been through a nightmare. It was pretty terrifying. The couple from South Padre Island that were so calm and collected at first and reassured us that there was absolutely nothing wrong, that they'd been through many of these, they were shrieking and panicking and literally freaking out. The look on their face, the look of horror on their face was kind of all we needed to think, okay, this is real. Because they said, no, they've never experienced anything like this at this point. Everybody was collectively terrified. And we just sat frozen in the hotel against the wall. We had no idea what to expect. Everything was intensifying. There was do we fear for our lives? What's gonna happen? Are we gonna make it through the night? Nobody knew. It was just kind of, I'd say, organized chaos at that point. I've never felt anything like that in my life, no.
In the early morning hours of September 16th, after spending the night inside the hotel ballroom, resort guests awakened to an eerie silence outside. Hurricane Odil is gone.
But around 6 a.m., the hotel staff started to go out and assess the damage done. And then about 8 a.m., they let us step outside. And it was, I don't think anything could have prepared us for what we saw. It was like landing on a different planet entirely. The hotel was completely destroyed. And the strength of a storm could do that much damage was There's no words to describe it really. I think that was at that point where I was just in awe of what had happened and the power of those types of storms. There was furniture in the hotel fountain, cars flipped over. It was unreal. I've never seen anything like it at that point. Our room was one of the ones that was not entirely destroyed. We were allowed to go back there if we wanted to. However, just because it wasn't destroyed doesn't mean it was livable. There were still 3 inches of water on the ground. There was sewage and debris that had been sucked up through the toilet that was stuck to the walls. We really didn't notice until the day after the storm how bad the situation was. That was when we heard that the airport had been completely destroyed and that the marina was completely destroyed. Yeah, the roads were washed out and there were no cars to drive, amongst other things. But the more severe rumor was that we wouldn't be getting out of here for at least a month before they would be able to get the airport in shape to get people out of there. But the thought of being there a month, I mean, we didn't know, the thought of, okay, what are we gonna do for food, for water? What are our families gonna think we're dead? There was just a ton, thoughts were swirling. It was pretty terrifying.
But while Odil has moved on, the storm is not over.
Alors ce cyclone, il va se déplacer.
So this cyclone, it will move and it will have 2 ways to die. The first way is that if it ever reaches land, if it ever reaches land, it will no longer be above the energy source that sustains it.
Qui le fait vivre. Du coup, il va commencer à diminuer en intensité.
As a result, it will begin to diminish in intensity. And a second effect is if it ever encounters regions of the atmosphere where there is strong vertical wind shear. Let's say that the cyclone must be seen as a tube, and the top of the cyclone must not be separated from the bottom, otherwise it weakens it, it kills it. And if ever a cyclone encounters areas where it's suddenly sheared off, there, it'll also make it less intense.
Odil weakens after passing over the Baja Peninsula. It crosses the Gulf of California with rains that reach into Arizona and New Mexico, where it ends as a tropical storm. In total, Odil led to the deaths of 18 people and over $1 billion in damage during its 9-day existence. But what made this storm unique is that it rapidly intensified and changed course, taking everyone by surprise.
Odil was moving a little bit erratically. It was hard to forecast the track. There were a lot of question marks with the storms. The models, originally were suggesting that the storm stays out to sea.
When a hurricane forms in the west of the United States, it moves towards the west. So it goes to the ocean, it goes to Hawaii. It rarely comes back to the United States and Mexico. So Hurricane Odil is quite a rare event.
Odil was quite rare. It was only the 3rd major hurricane, Category 3 or above, to strike the Baja Peninsula of Mexico. Pretty rare in that part of the world. We don't see a lot of major hurricane impacts.
In Cabo San Lucas, food and water is rationed. The Mexican military performs food drops for the local residents. Resort guests worry their friends and families back home will fear the worst if they don't hear from them.
So the first thing on our minds was, let's get in touch with our family, try and rebook our flights. We'll be out of here tomorrow, maybe, hopefully. The Wi-Fi completely went out.
After being stranded for 4 days on the resort, the wait for these vacationers is over. They are finally going home.
There was word that some of the commercial airlines had started doing rescue missions, like Good Samaritan rescue missions. All we knew was we were going to go to the airport, wait on the tarmac, and get on a plane and go. No, because there was really no airport building, it was a tarmac. They had cleared up enough of the tarmac of the airport to just allow planes to take off. Once we taxied down the runway and we had, wheels up, everyone just started cheering. Everyone was cheering, crying. Great, we're going back home to our, first world lives, and these people are completely, everything's destroyed. They have nothing.
Many of the vacationers, now survivors, began a fund to help the community of Cabo San Lucas rebuild. The unpredictable nature of Hurricane Odil proves that scientists still need to know more about these storms.
Hurricanes, cyclones, it's a subject that speaks to everyone. We've all seen satellite images of cyclones, we've all heard about them in the media, but it's not something that is completely understood by researchers. And this makes it all the more difficult to predict what will happen to them with climate change. It's a really complex issue.
It is up for debate if climate change will produce more hurricanes in the future or not. The models generally suggest that the number of hurricanes may not really change, but the hurricanes that do form may have a tendency to become stronger.
In regards to the influence of climate change on the trajectory of tropical cyclones, on their size, on their speed of movement, there is no clear answer to this. That is to say, the forecasts for the moment are too different to be able to be conclusive on this question.
But most scientists do agree that this destructive force of nature will only get worse and more unpredictable. Recent findings show the average forward speed of hurricanes has been slowing down as average global temperatures warm. When hurricanes stall in one place, they produce huge rainfalls and severe flooding as water rises to record levels. In 2017, Hurricane Harvey sat over Houston for 4 days and dropped over 2 meters of rain in some areas. 68 people were killed.
Another impact that we may see with a changing climate is rapid intensification of hurricanes, especially as they're near the coastal areas. This has a lot of impacts and makes it hard to prepare for them.
The coastlines, they're getting more and more populated, more and more developed. In addition, with climate change and rising water levels, the risk of submersion in the event of a tropical cyclone will be increasingly high. The most effective and radical solution would in any case be to encourage new construction to be carried out further away from the coast.
On September 8, 1900, a 16-foot, about a 5-meter wall of water pushed across Galveston Island, killing 6,000 to 8,000 people when a Category 4 hurricane made landfall. Most people died from the saltwater storm surge. It devastated Galveston. Much of the island was destroyed, and so soon after that, a seawall was built, really protecting the island and protecting the city of Galveston from the tremendous waves and water that can push in during hurricanes.
Walls to protect from rising seas may become part of a future hurricane defense. The statue on Galveston's seawall is in memory of the Great Storm of 1900. It ranks amongst one of the largest hurricanes ever recorded, making it the hardest to forget. On the list of hurricane names, some are retired. There will never be another Sandy, Katrina, or Odil.
Hurricanes or tropical cyclones that have caused too much damage are removed from the list. So we will never have Hurricane Katrina again, never again have Hurricane Matthew. These are names that have been removed from the list because they have too many bad memories.
And for some, those memories can last a lifetime.
There was genuine PTSD that lingered when we got home from the storm, from the hurricane. Any little noise you hear, or if you hear someone passing by your window, complete jumping, because you're constantly on guard. And it took the three of us a very long time to get back into that normal life. An experience like that stays with you forever. Well, first of all, opened my eyes to what the power of nature and what a destructive force it can be, and the strength of a storm like that. That was one of the most intense, terrifying experiences I've ever had in my life.